Okay, so in this video I'm going to talk about the trapezoid approximation rule and how it relates to Riemann sums and specifically a set of information, a data chart that I found on the World Bank. So what I did, I went on the World Bank and I was looking for something that was interesting to me, and that would provide a graph that I could use for this project. And what I came upon was hospital beds, and I was looking up medicine related topics today in the U.S. and how it compared globally, and I came across this statistic and this chart that ranked hospital beds per 1,000 people, and it does it for every single country in the world. And there is some inconsistencies in the information. There are missing years, but for the most part, there is over 30 years of information on this one topic. And so I looked at the U.S. and I realized something, that over the past 20 years, hospital beds have declined quite significantly. And I think that what it's due to, and I know from research what it's due to at this point, is that the global advancements in medical technology, specifically in the U.S., have outdistanced the capacity of the service of the clinics in which these technologies should be applied. And so while the facilitation of this research has increased, the average number of hospital beds per 1,000 people in the United States has declined steadily over the past decade due to this exponential population growth that has occurred over the past 20 years. And so with this idea in my head, I took the data chart for the U.S. from the years 1990 until 2010. And within that, there are two inconsistencies. In the year 2004, there was no data, and for the year 2010, there's no data. But if I look at the slope of the years previous, I can make a very accurate estimate. So it's not a problem. And I took this data and I made a graph out of it. And this is what I'm going to put up. I'm going to put up the specific data chart and the graph that I made. Okay, so the information that I put up here is the year from 1990 and 2010 to 2010, and the beds per 1,000 people. Now, what that means is that per 1,000 people, say in 1990, there are on average 4.9 beds. So, in the grand scheme of things, when you think about it, that's not a lot at all. Five beds maybe per 1,000 people, and it's really unpredictable, since people can need those beds at any given time. It can't be really very accurately predicted how many people are going to need hospital beds, and how many people are going to fall ill or have an accident, and their up years and down years, as I noticed through research. And so next I'm going to put up the graph that I made from this data. Okay, so here's the graph, and I made the data a little bit smaller so that we could fit this in, because what I'm going to do is explain the trapezoid approximation, how this works. So we all know what Riemann sums are, and at this point, and Riemann sums, let me go to get a marker. So Riemann sums are a pretty good indication of volume or space area underneath the curve, or underneath the function. But they're not that accurate, and that's why there are left-hand Riemann sums and there are right-hand Riemann sums, and there are midpoint Riemann sums. And what the trapezoid rule is it's a better version of Riemann sums. It's an average, as I'll show you. So we have this graph, and what I'm going to do is do this as if it was a Riemann sum, but as you see here, I have a little box that says 11 subdivisions. So that's what I'm going to do. I'm going to space it by 2 years. So I'm going to start, and you'll see where we get the trapezoid from. So to there. There we go. It's a little bit off, but it's not a problem. This is our first box. This is our first trapezoid and our trapezoid approximation. So what I did, I went to this first dot up here, this first point, and I drew a straight line down to the second point. That's a more accurate version of a Riemann sum. And if we were to do this as a normal Riemann sum, then we would start at this point that I indicated and go straight across if it was a left-hand Riemann sum, and then straight down. And obviously that would leave room for error in this area right here. And if we were doing a right-hand Riemann sum approximation, we wouldn't even have this this line right here. So as you can see, this is sort of a fusion of the two, and it's much more accurate. Okay, had another little technical difficulty, but now we're on track. So now you understand that I'm going to be drawing these trapezoids all along the graph, all the way along it. And this is, like I said earlier, is going to be a much more accurate form of integrating this formula. So I'm going to draw these in, each one of these approximations. And I'm gonna pause the video because this might take maybe a minute. Okay, so what I tried to do here was indicate to you that each one of these rectangles, the difference between each of these are trapezoids. And if you notice at 2004, right here, and at 2010 there's no data. So that's at this point right here, and this point right here. And what I did to fix that was I took the slope of from 2002 to 2003, this section right here, and I carried that along through 2004. So it's a pretty accurate prediction. It was similar, I think, from my 2004 data. I made it 3.2 because that was in line with the 2002 to 2003 slope. So that's 3.2, and I made my 2010 slope 2.9. It's a little messy, you get the idea though. Okay, so the next part of this is we need to find the area underneath the curve. That's the whole point of the Riemann sum or trapezoid approximation. So the next step is the actual math, and I'll show you how to do this. So when we're taking the area of a trapezoid, hopefully you learned this in geometry, it is the area equals, oh, I'm going to do this somewhere else. The area equals one half height 1 plus height 2 times the width of the trapezoid. So let's take an example. Let's go this right here, from 1990 to 1992. My first trapezoid, my first 2-year trapezoid. So on the graph, the area would equal 1 half times height 1, which is this point right here. And if we look to the chart right there, we can see that at 1990 it's 4.9, so 4.9 is the height, otherwise known as f of 0, plus f of 2 at 1992, which is, if we look to the graph or the chart, 4.6. Then we multiply that by the width, which is going to be 2 all throughout. And this right here is the area of that first trapezoid. So it's not too hard. We just have to do that for each one of these subdivisions. So all 11 of these subdivisions. Actually, there are 10 subdivisions. I did my I did my math a little wrong. Not a problem. So let's get started on this math. I'm just going to take this out. So the area, once again, 1/2 h1 plus h2 times the width of the trapezoid. Okay, so I'm going to write this out. So since our width is 2, it's quite convenient that it is 2, because since we have to multiply by 1/2 on the outside of the h1 plus h2 as the trapezoid, as the area of the trapezoid requires. And the reason that it is, by the way, is because we're taking the average of height 1 and height 2, and that average is the average width of it. So what we're going to do is, since that 1/2 is multiplied, and then our width on the other side of the h1 plus h2 is 2, it's great because we don't have to add that 1/2, because 1/2 times 2 equals 1. So 1/2 times 2 equals 1. So it would just be 1 times. It would just be 1 times h1 plus h2, which would equal h1 plus h2. This would not be. Let's try that again. It would just equal h1 plus h2. So because of that, it's quite the space saver. We will be able to. Okay, with all these technical malfunctions aside, I'm going to show you how to do this quickly and efficiently, and then we'll get into the answer. So for the first step, I'm just going to erase this information right here. So now that we have this simplified version, because our width is 2, which is, like I said earlier, very efficient for us, because we don't have to multiply by 1/2. We're going to be able to do this more quickly. So I'll do the first 2 trapezoids for you, just these 2. And what we're going to be doing, if this wasn't already made clear, is we're going to be going down through this data chart, and we're going by every 2 years. So from 1990 to 1992, to 1992 to 1994, from 1994 to 1996. And you can see on the bottom of this chart, you can see where each one of the lines is perpendicular to the line that I just made, and it is at the even points that I just referred to. So the first trapezoid that we're going to do would be this first one, and it would be from 1990 to 1992. So we look at that at the chart, and we see that at 1990 it's 4.9. So without our 1/2 and without our width, which is 2, it will be 4.9 plus 4.6. There we go. That is our first trapezoid. And really, like we were talking about earlier, it's times 1, because 1/2 times 2. But that's irrelevant. So for our next trapezoid, all we're doing is adding these up, because we're eventually going to find the area underneath the function. And so for our next, we have from 1992 to 1994, 4.6 plus 4.3. And if you might have noticed, these two are the same, and that is because once you go down the list, what the height 2 was previously, that becomes the height 1, because they're all touching each other. So we want that. So there's no room for error in between these. So this here is height 2, and this is height 1. So it's quite simple. We're just doing that throughout every single trapezoid, and once we get to the bottom, we add them all up, and each one of these segments up. And now I'm going to do that, and I'll give you